Consuming GraphQL application programming interfaces requires a client that handles three core tasks: schema parsing, code generation, and normalized caching. For robust cross-platform development targeting both Kotlin multi-platform and native Swift, Apollo Client is the definitive choice. Relay, while powerful, is tightly coupled to the React component lifecycle, making it unsuitable for native mobile stacks. The client must first pass the GraphQL query document into an abstract syntax tree. This AST is then used by the code generator to produce type-safe models. This process eliminates runtime errors associated with manual JSON deserialization. Network responses are immediately mapped to native language objects, such as Kotlin data classes or Swift structs. This type safety is mandatory for maintaining large mobile code bases and ensuring compile-time validation of all network operations. The GraphQL schema definition file is the single source of truth for client code generation. You must download this file, typically named schema.json or .graphQLs, from the server endpoint using introspection. For Android and Kotlin projects, the Apollo Gradle plugin requires configuration to locate this schema file. Simultaneously, you must specify the directory containing all operation documents, which are the .graphql files defining your queries and mutations. On the iOS and Swift side, the Apollo command line interface tool is integrated directly into an Xcode build phase script to execute the same task. Code generation transforms these GraphQL operations into executable, type-safe classes. Examples include fetch user query or create post mutation. These generated classes encapsulate all necessary input types and define the exact structure of the response payload. This code generation step is strictly mandatory and must execute successfully before the application can compile any network operation. Client initialization requires two specific parameters: setting the base uniform resource locator and configuring the underlying hypertext transfer protocol stack. On Android, this typically involves OKHTTP. On iOS, URL session is standard. Define your basic query, such as fetching a list of items, within a dedicated .graphql file. Once generated, instantiate the corresponding query class. Execution is performed using the execute method, which must be handled asynchronously, usually within a Kotlin coroutine or using Swift's async await pattern. The resulting response object is strongly typed and contains the data payload or detailed error information. A critical step is data mapping. You must transform the generated response objects, which strictly mirror the GraphQL structure, into application-specific user interface models. This separation ensures that your user interface components are decoupled from the network layer's generated types, improving maintainability and isolation. Normalized caching prevents redundant network requests by storing data based on unique identifiers. The cache uses a composite key derived from the object's mandatory double-underscore-type name field and its unique identifier field. For instance, an object identified as typename user and identifier 123 is stored under the key user :123. When a subsequent query requests fields for this specific user, the client first checks the cache. If all requested fields are present, the network request is entirely skipped. If only a subset of fields exists, the client's fetch policy determines whether a partial fetch occurs or if the cached data is returned immediately. Objects that lack a unique identifier field are not stored independently. Instead, they are stored as a nested part of their parent object's cache entry, maintaining data integrity within the graph. Structure. The default normalized cache operates solely in memory, meaning all fetched data is lost when the application terminates. To enable true persistence, the cache must be backed by disk storage. This typically utilizes an underlying SQLite database or a similar key-value store provided by the client library. Configuration requires specifying the maximum cache size, for example, 10 megabytes, and defining the exact file location within the application's sandbox directory. Implementing disk persistence involves wrapping the existing in-memory cache instance with the persistent store implementation during the client initialization phase. This configuration ensures that the cache state survives application restarts, which is mandatory for providing robust offline capabilities for all previously fetched data and improving startup performance. Fetch policies govern the interaction sequence between the local cache and the network. The CacheFirst policy attempts to fulfill the entire request using only cached data. If any required field is missing, the client falls back to executing a network request. Network only strictly bypasses reading from the cache, but always writes the resulting response back into the cache for subsequent operations. CacheAndNetwork is used for optimal perceived performance. It immediately returns any available cache data to the user interface while simultaneously sending a network request in the background. The user interface then updates again when the fresh network response arrives, ensuring fast initial loading followed by eventual consistency. Selecting the correct policy is crucial for minimizing unnecessary network traffic and optimizing performance, especially when users rely on mobile data connections. Mutations modify server-side data and require immediate local cache updates to reflect the change without forcing a full data refetch. Optimistic updates are a technique where the client writes the expected result of a mutation directly into the cache before the server response is even received. This provides instant user interface feedback to the user. If the mutation subsequently fails, the optimistic data must be automatically rolled back by the client library. For complex data changes, manual cache manipulation becomes necessary. This involves utilizing the client-specific cache application programming interface, such as write to cache or read from cache, to explicitly update, delete, or insert records based on their normalized keys. This manual intervention is essential to guarantee that the user interface state remains perfectly consistent with the server state immediately following the mutation execution. Robust error handling requires differentiating between two distinct error types: network errors, such as connectivity loss or Hypertext Transfer Protocol 500 status codes, and GraphQL errors, which are returned within the dedicated errors array, indicating issues like validation failures or authorization problems. Network errors trigger standard retry mechanisms or transition the user interface to an offline state. GraphQL errors mandate parsing the errors array to extract specific codes or messages for precise user feedback. In production environments, ensure that sensitive details, including stack traces, are strictly suppressed in client logs. The final deployment checklist requires verifying that the client is configured to use production endpoints, that logging levels are set to minimal, and that appropriate security headers, such as authorization tokens, are correctly attached to every request via interceptors.